This is Self-Directed Research. After a bit of a hiatus, we're back for Season 2. Make sure to like, follow, and subscribe wherever you find us to stay up to date. And as usual, visit sdr-podcast.com/episodes for all of the presentations, videos, show notes, and transcripts. This episode is sponsored by Depot. Listen at the end for more information. In this episode, James presents Proxying is Just Dumb Routing.
I think everyone's okay. Can you hear me fine, James?
I can hear you just fine.
Cool. All right, James. Welcome back to Season 2 of SDR. What do you have for us today, James?
So have I ever told you that my brain thinks in terms of like X is just Y? Like that's kind of integral to my learning experience is I go, oh, this is like that other thing.
I have noticed that, yes. So proxying is the Uber of routing, is what you're saying?
I don't know how to pitch this as a startup deck. I've been working a lot on proxying both for River and then PostStation, this app that I'm developing for embedded systems, is also very proxying based,
right,
in that it's kind of the bridge to all of your devices and things like that. I think I've even mentioned on episodes before, I've tried to make a routing or a whole networking stack, really, and routing is a pretty important part of that. And always kind of like, there's always something where I got my feet tangled up on, and routing is one of them. And so I ended up leaning really hard into proxying for PostStation and kind of realized after I had everything wired up that I actually got real close to what you would want out of routing. So today is just proxying is just dumb routing.
Okay. But, like when you say proxying, I think about, HTTP proxying. Is that what we're going to talk about today? Or are we talking more low-level stuff like postcard RPC based?
I mean, it's going to be around postcard RPC because that's literally what I've been doing since the last time we recorded an episode is...
Sure, but you are also writing a reverse HTTP proxy, so that's, I don't know.
It's true. But yeah, I mean...
That's where my mind goes. That's why I ask these questions, James, but sure.
Effectively, they're very similar, but routing does a lot more. So it's almost like proxying is just kind of a sort of subset of routing. So like normally when we're talking, exactly like you're talking about HTTP devices, the internet, we've got computers everywhere, and your computer doesn't know exactly how to get to Google servers or to get from my computer to your computer because all other computers are just somewhere else. Even on your computer, the answer is just it's somewhere else. When we send a message or a packet or something, we just send them to somewhere else. We say like we have a vague idea, like when we do DNS, we might get an IP address, and then we kind of just write it on the outside of the envelope and drop it in the outgoing mailbox and hope it gets there. We really, like, the computer has no idea how it gets there, but it knows the destination and it just says go. And this is like generally how any computer can talk to any other computer, as long as you have some concept of the destination, like an IP address or DNS address that gets turned into an IP address. You just kind of yeet it out onto the internet and it gets to the other side because routing is the thing that figures it out. And routing is one of those, like, it's a whole thing topics. Like, there are many
it absolutely is.
PhD careers in engineering and company whose entire jobs are to just think about routing, of how you manage that. And a lot of it comes down to, like, you only have so much overview of even an IPv4. You've got 32 bits, 4 billion addresses. If you had to keep information on all 4 billion of those devices up until maybe the last decade or two, that would be very difficult. And now that there's IPv6, it's, even more outstandingly difficult.
And so much of the knowledge around routing is kept because not many people really need to know about it. I've been in some circles where people have said, it's always DNS when something goes out, there's an outage on the internet. But then you run into some deeper circles of hell where people say, if it's not DNS, it's BGP. And you're like, wait a minute, what's BGP? And then people found out about BGP because of some major outages. But then when you look at how it's actually done in the big router companies, and it's frightening. It's very scary.
And routing is another one of those things where there's like, as it's described by the RFCs, like the internet RFCs for them, and then there's what actually happens in practice in the same way that you can send certain packets and it's totally valid according to the RFCs. But if you ever go through a Cisco router somewhere in the middle, it'll just drop your packet because it's technically allowed, but it just says, no, get out of here.
Yep.
And so there's also like those kind of things. So but like the big takeaway here, like you said with BGP, is there's this whole system where every machine that your packet kind of goes through, every district office that it bounces to on the way to its destination, they all have sort of a partial view of the internet, usually like their direct neighbors, and then maybe some big picture things. That's where like BGP comes in and things like that. And they'll have routing tables, and no one ever has a complete picture of, or most commodity hardware has no idea of the entire internet. They just have like, where is the next step? And then maybe like some big picture version of that.
Well, and the thing is, there's no, when I looked into traceroute and that kind of thing, first of all, traceroute is not representative of how packets are actually routed. There's something I discovered recently. There's a whole page about how it's actually freaking useless. And if you notice that there's drops somewhere, it doesn't actually mean that there's a problem there. It could just mean that they're ignoring your ICMP packets because they are big routers and they have other stuff to do, like routing actual traffic.
Was it Mara or someone made a traceroute implementation that made all of the times go backwards, because it's like exactly what you're saying is it's just a payload in a packet, and turns out you can lie on the internet and you can just put the timestamp in history.
There's different techniques. Because it's just a TTL. Traceroute with ICMP packets is a hack. So routers are not obligated by standards or whatever to actually respect that. You can do traceroute by UDP, but then that's not the same thing as TCP, which is what most applications use. That's not true anymore because of HTTP3, darn it. The place I was getting at was that...
You were too quick to say that.
It's freaking Google.
For Amanda, Quick is the original name of HTTP3.
Oh, I didn't even freaking catch the joke. Well played, James. Touché.
I'm glad I explained it.
As the Americans say, pretending to be French. Touché.
That means it's staying in the episode.
It probably is. I had another point, I swear. Traceroute, something. Yes. Oh, there is no, like, because it's distributed systems, and I'm sure you were getting to this, and I'm stealing the limelight on your episode, but there is no one version of the truth.
Yeah.
Studying the internet is being a historian. I don't know what's the closest thing, but you just go around and you try to ask questions of things and gather data, and you have some incomplete, ever-changing version of the truth. And depending on where you stand when you ask a question, you get different answers. And you don't know what's going on in certain countries. There are in different countries that have different policies about different things.
Yeah. And it's one of those things. It just takes effort, and it's how the internet has evolved. It tends to work fairly well, but it means that you need to have sort of an idea of where things are, and you need to keep track of that because they do change over time. And for embedded devices, particularly small devices, that's state and things that you have to do to keep up with figuring out where they are. You know, I heard this report about this, but has that timed out? Have I gotten newer conflicting information? Figuring out all these things. So you've got your little device that's a sensor or whatever, and it wants to send something over the internet. You have to go, okay, I would like to put a destination on this. Where do I send this? And in some cases, it's just hard-coded. You just send to a place and someone else will figure it out. But if you'd like to do any kind of networking locally where you're like, well, sometimes I send it over here over my wireless network and sometimes over, the serial bus that I have over here, you kind of have to keep track of some things. And that's not always easy for small devices. It's very possible. You can get little Wi-Fi devices and things like that, but like a TCP/IP stack that does the bare minimum of routing takes up a non-trivial amount of your CPU cycles and memory and code storage and things like that.
And it's probably way overkill.
Devices are going that way. What was overkill a while ago, devices are getting fast and cheap and powerful. So
I guess so.
Yeah.
Have we talked about Collapse OS on the? I'm sorry to hijack your presentation once again.
No, I don't think we have. I've seen a bunch of projects like that though. Is that the one that like bootstraps from Forth, or is that a different one?
I think it's a different one, but I see the one you're thinking of. Mine is just if there is an apocalypse and we suddenly live in a post-apocalypse world, we are going to lose computing. And it's a shame because for modern computing to exist, there's so many prerequisites. But what they notice is that even though we're probably not going to be able to make chip from scratch again for a very long time, if ever, there's a ton of 16-bit chips that you can scavenge from a lot of different equipments. And so they're developing for that, essentially. It was like you go around, you get 16-bit chips from various places, and you can actually assemble them manually with like wires and stuff because it's still like this, what is it called? Is it pinball package? I don't know exactly what it's called.
Are you talking about like DIP ones that have the dual inline package?
It's still human scale. You can work it with your fingers and like connect them to things, and that's their premise. And I remember needing to take a minute after finding that website, like, wow, some people have put them. When I see doomsday preppers with a lot of canned goods, I'm like, this is gonna last you 2 weeks, and you're gonna get eaten by your neighbor.
I was gonna draw,
whatever.
Yeah.
But when I see that, I'm like, that's more realistic and more scary to me somehow.
Yeah. It's challenging. As someone who likes building the world from scratch and does it as a hobby, there's a lot to build, especially if you're at the point where you can't just buy things off the shelf either. Yeah, I've seen that, and I've seen a couple of other ones where you're like, okay, if I can get something that can compute some numbers, how can I work back up? And I've seen one that bootstrapped itself from like assembly to Forth to Python, and then maybe a C compiler at some point in there, where if you have some kind of device that can run Forth, or if you can write enough assembly to get a Forth, you can write enough Forth to get a Python, and you can write enough Python to make a C compiler or something like that. It was an impressive set of bootstrapping.
But James, why would you want a Python? I'm sorry, this is such a weird step. I can forgive C, but I draw the line at Python.
C? This is not the right podcast. It's a different one. Different podcast for Python.
Okay, so if I'm going to make the claim routing is too hard for these small little guys that I write code for, then what about proxying? So we've talked about proxying. Most people have probably heard of proxying if you've done back-end stuff. Proxying is the Nginx, the River, the Apache 2 that you put in front of your production servers.
James, I like you, but did you just sneak up your own work between those? You could have mentioned Caddy. Caddy's mainstream-ish.
Okay. Yeah, I probably shouldn't, because I'm not actively working on it right now.
But do you want to mention why?
All right, I'll take it again.
No, you can. No, let's keep it. I'm just saying, do you want to mention why it's advised to have a proxy in front of your web application?
You would probably know better than I would, but I just want to talk about what proxying is first.
You can do that.
Proxying in general is you put a computer in front of your computer. When a client wants to talk to who they think is the server, what they end up talking to is a proxy who gets their first chance to either terminate the TLS connection, to do some kind of security check to say, hey, you're asking for things that you should not ask for, to do authentication. And then usually that proxying agent is sort of like a bouncer. And if they decide to pass that on, then they're going to pass that on. And they can also do the job of load balancing. There's a lot of different reasons you'd use it for proxying. So that first server might just say, okay, well, I've got 10 people in the back. You're going to go to desk number 4 to get your request served because they're the least busy.
In the explanation you just gave, there is one word that gives away that you have been working on a reverse proxy. Do you know which one it is? Terminate.
Terminate? Yeah, it's a good
because
one.
when you tell people, I'm going to terminate your connection, what they think is you're going to cut it off.
Yeah.
But what it actually means in that context, terminating TLS, means we're going to do the last bit of work that takes all the HTTP traffic and encrypts it and decrypts it.
I think this is one of those old telephone network rules, because when you talk about
probably
terminating like a connection, it's like literally where you've connected it onto some device or something like that. So I think
the last mile or something. Yeah.
Yeah.
I was just putting myself in the shoes of someone who's not worked on such a proxy, because we both have. And that's the word that stood out.
This is also very helpful for me, because that's exactly how I was picturing it until you explained it to me. So thank you.
Thanks, Amanda.
Gotcha. Yeah, and so really it just means there's a computer in front of another computer is proxying. It means you are transparently talking to something in front of what you actually think that you're talking to. And in a lot of cases, this isn't even exposed. You wouldn't know. There's no like hint, hey, I'm talking to a proxy. The idea is that ideally, most of the time, it just is transparent. And this gets used a lot on the internet for client-server interactions. When your laptop connects to a server somewhere, it's the client, and the server is the server that it's talking to. And these get used a lot for proxying because when there's this direction to it, it means that when you go in, you talk to the bouncer, that gets passed on. The person on the inside passes it back to the bouncer and back. If you were doing a true peer-to-peer connection, it's a little more difficult. Then you're kind of a full-blown router at that point, because you're doing kind of like anyone-to-anyone connections, where proxying is more specifically like someone on the outside comes in, gets bounced to someone privately on the inside, someone on the inside privately replies, and then that gets taken back to the client. There's other cases where this isn't the case. If we're talking about more proxies, there's like internal, what are they called? Sidecar proxies get used a lot, and that's for like mutual authentication, where you both have your own bouncer that sets up a secure connection between you and things like that. But that's a totally different topic.
I was confused about that for the longest time, so it's possible that I'm still confused about it. But I think you're defining reverse proxies. You're thinking of the thing that is like Google frontend, or you mentioned Nginx or something that often has one or a few websites behind it. There's also forward proxies, but those are not as used as they used to be. Wow, that's a lot
Yeah,
of
that's
use.
true.
They used to be used to accelerate connections. You'd have you'd run Squid locally and it would cache the internet for you and it would just be
Yeah.
served from disk instead.
I think like internal business networks used to use those
I
too.
think some still do.
Like all your outgoing connections went through a bouncer and things like that. So yeah, you're right. I'm mostly talking about reverse proxying,
think
but there are definitely a couple flavors of proxying.
And I'm just going to answer my own question because I raised it. The one of the reasons you might want you do want a reverse proxy is because your application probably only speaks HTTP1 first of all, but you want to serve HTTP2 and 3 to the outside. You're not going to want to worry about TLS.
Translation is a big part of it.
And thirdly, performance also. If you have a bunch of different nodes around the world that can do the TLS handshake with your clients and then talk to your application, even if your application itself is only in one location, that's still going to speed up the initial handshake and exchange. And then also just because the internet is a scary place. Like when the internet first started, before everyone got on it, it was just like, yay, we can exchange information. But now it's as soon as an IP comes live and starts accepting connection, it's like, are you a PHP thing? Can you leak credentials? I'm going to try all the known paths.
Are you a WordPress thing? Yeah. I love seeing those in logs for like a bare HTTP server. And it's like,
I have so many of these.
WP login admin. Like,
so instead of people attacking your application directly and potentially finding, I don't know, something in your Python code that makes it uses up all the memory, something in your C code that crashes and dumps private user data, you'd rather have them attack Google or Amazon or whatever you put in front of your website.
Exactly. Yeah. And a lot of times there tends to be a lot more security hardening. If people use commonly popular reverse proxies like Nginx or Apache, there's a lot more work that goes into hardening those, where sometimes people put very squishy application servers behind them that go, I haven't thought of all the edge cases like buffer bloat and all of those.
Absolutely.
And you can just configure the, instead of having all 100 of your servers be immune to the same, you just have the bouncer.
But on a personal note, I think it's absolutely bonkers that Nginx is still the default choice for a lot of people when it's written in C. I personally, I'm on the record as like the Go hater, and I use Caddy. Because I may hate Go, but at least it's memory safe. So okay, I'm losing out on 10-15% performance, but I don't know, it feels better.
Yeah, so I mean, we have this sort of proxying setup where there's that bouncer in the middle. So we have this sort of setup where the client talks to the proxy. The proxy, in this case, appears to be the server. So it's acting in the server role. But as soon as it's received that request, if it decides to move on, it then turns around to the inside and it makes a request to the real server. So in that role, it's a client. So it essentially kind of does both. It pretends to be a server to the outside and then turns around and pretends to be a client. So we get the server talks to the proxy talks. I screwed this up. This is what I get for skipping around slides. And then in the other way, when the server replies to the proxy is the client, and then it turns around and pretends to be the server. So we just pretend at every step along the way that this is a direct connection. So in this case, the internal server knows nothing really about the real client unless the proxy passed it on. And in the same way, unless the proxy passed it on, the real client knows nothing about the real server, which gives you sort of this, blinders you can put on where you just say, it's just a direct peer-to-peer communication of a client and a server. How more simple could it be than that? The thing is, we can also use this for embedded devices. And this is exactly what I'm doing with PostStation is instead of having networking and things like that on the inside, we make things cheaper by saying, well, these devices could already do point-to-point connections. You could connect to them directly. And what PostStation introduces is, okay, well, I will be your delegated proxy for this. So then PostStation is in charge of talking to the actual embedded devices, can speak with them in whatever protocol they'd like. And in the same way you were talking about the difference between HTTP1 or whatever, it speaks exclusively a very compact binary format of postcard to these devices, but you could have your clients speak JSON and REST to PostStation, and it will do that translation for you and pass it on. And so we can make a lot of things cheaper because we don't have to think about routing. We don't have to think about, sending JSON to a tiny microcontroller. We don't have to worry about any of those things. But the downside is I said that proxying, at least reverse proxying like we're talking about here, there's no real any-to-any comms here. Like if you want a device to talk to a device and they're in this perfect little simple brain world where they only take incoming connections from one direction and then all replies go back in that direction, it's more challenging to say, hey, please send this to a specific person, which if you've set up all of your devices to say, hey, I receive commands and I publish things, everything coming in goes that way and everything going out goes that way and life is simple, it's great. But if you really do want peer-to-peer networking, then it makes things a little bit more challenging. But often for most microcontrollers or things like that, that's good enough. You might have like a small network of devices, but they're all doing their job. They're running the elbow, the wrist, and the hand motors. And the elbow doesn't usually need to talk to the hand very often. They're usually all talking back to the brain, and the brain is talking back to all of the motors. Yeah, this is usually good enough. Like I said, for website backends, you're usually going client to proxy to API server and back down the line. That's like the people who have worked in backends, that's how they think. But for embedded systems, it might be more like your PC is talking to some serial port or RS-485 bridge, which then is talking to a device. So before I was talking about a client talking to PostStation, talking to the embedded device. And the cool thing about proxying is you can proxy multiple times, because you don't necessarily have to know, because I said it was transparent, you can proxy multiple times. So I could proxy from my computer application to PostStation to USB to serial port adapter firmware that is then talking to another device on the far side of that, or some wireless adapter or something like that. And both of them can be very, hey, mush brain, I don't have to know what the entire network looks like. And so you end up with this, a proxy of a proxy of a proxy of a proxy, where instead of being that iconic like internet picture of every node connected to every node, you get this directed acyclic graph of networking, where as long as you're always going downwards, you can go down until you actually hit the node you were looking for, and that node can then fire the communication back up the line, and it always ends up back at the client that it was interested in talking to. And this is one of those things I did over Christmas break, is I wrote a wireless protocol for devices around my house so that now I can talk from my computer to PostStation to the adapter over the wireless network to the wireless device, and it can talk all the way back up to me. And I don't have to know that there were however many hops there are in that, but it all still generally works.
There we go. Like, don't hold me accountable. Don't hold me liable for any of this.
Yeah. But yeah, I try to not get too deep in the slides so we could actually talk about stuff.
Sure.
Because there's some fun side effects to this. Can you see the other price you pay when you don't have a routing table? If proxying is like taking the envelope and putting it in another envelope to pass it on, when you end up doing this proxying multiple layers deep, instead of having a routing table, you end up having to build this stack of nested envelopes that have the address on each side. And so if you want to go to a destination that's 6 layers deep, you take your envelope and put it in an 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 envelope, which I haven't decided if I love yet. It's simpler for the devices in the middle because they just take the envelope out. Do I know this person directly connected to me? Yes, pass it on. No, just throw it away or bounce it back. So they don't have to keep track of routing. But if you go more than a couple hops deep, essentially you're putting like a MAC address on every layer. Yeah. And so you end up paying that. But my hope is that most of these networks are fairly shallow. Like I can't think of very many use cases where you'd go more than 3 or 4 deep. But
plus, I can't imagine the envelopes being that big, right?
Right now, well, for Postcard RPC specifically, I use 8 bytes or 64 bits as like the unique ID of devices. So I end up needing to stick that and then 1 byte that says this is a proxy message in each one. So it's 9 bytes on every hop, which for us doesn't sound a lot. But when you have like little tiny wireless networks or serial port networks, that adds up pretty quick.
You know what you should do? You should reserve one value. You should have a niche value for this is not a proxy message. And then you can save 1 byte on every message. It's not a joke. This is an actual protocol design.
So how Postcard RPC works in this case is you have messages that have unique IDs. So what I do is I hash the schemas and get the IDs, and then you figure out if there's a, I do the perfect hashing of that. So proxying ends up just being another kind of message. So the actual header on that is just that. So that was the 1 byte. You're kind of already paying for any kind of messages, because in my networks, I'm also talking directly to the bridge device as a real device. And also it has an endpoint that says, please pass this on to your friends on the other network, those kind of things. So that one's free, but I still have to include the serial number on that. Although I could maybe be smart and then do a mapping of, I don't know. But then it just becomes a bad routing table. I think I have to draw the line somewhere.
Yeah, I was gonna ask, like, do you do var int encoding, which is where even if you can technically have up to 64 bits with integer, you don't always send 8 bytes. You can kind of, like, smaller integers take fewer bytes, but it doesn't make sense for IDs, right? Because they're more like unique IDs,
No.
random values.
You assume that they're
Yeah.
randomly distributed. An 8-byte value could technically be up to 10 bytes,
Right.
or you only get 7 bits per byte when you use a varint, because everything else in Postcard is varint, but this is specifically an array of 8 bytes, just so I don't pay the varint costs. Because in many cases, if you had the top bit set, just like the highest bit set in the serial number, then all of a sudden now it's the largest varint because it has the highest max value. So
Varints are easy.
Yeah.
They're like UTF-8, but for numbers.
and
That explains everything, I think. I think we're all clear on that now.
yeah, and it turns out they're actually really fast. And this is probably just like an artifact of computers being optimized for this, or at least on desktops, they're so memory IO bound. The cost to actually just sit there and iterate over the top bit and things like that is actually astoundingly. I tried a bunch of clever other variable sized integers other than like the classic varint or LEB64 that like Protobuf uses and whatever, and it was like a negligible difference even if you were doing something. It's one of those things where if you look at it, you go, that's got to be way faster. Super scalar architecture punches you in the face every single time you make assumptions like that. But yeah, proxying, it's good for you.
All right. This episode is sponsored by Depot, the build acceleration platform that's on a mission to make all builds near instant. If you're tired of watching your builds in GitHub Actions crawl like the modern day equivalent of paint drying, give Depot's GitHub Actions runners a try. They're up to 10x faster with unlimited concurrency, faster caching, support for Linux, macOS, and Windows, and they plug right into other Depot optimizations like accelerated container image builds and remote caching for Bazel, Turbo Repo, Gradle, and more. Depot was built by developers who were tired of wasting time waiting on builds instead of shipping. It's made for teams that want to move faster and stay focused on what actually matters. That's why companies like PostHog use Depot to cut build times from over 3 hours to just 3 minutes, saving tens of thousands of build hours every week. Start your free 7-day trial at depot.dev and let them know we sent you.